Thank you very much. I'm Jordan. Like Wyatt said, nice to meet you all. Today I'm going to talk about DataFusion Comet, specifically writing Iceberg data in it. So just before we get started, a little quick about me. Sometimes I make low quality data YouTube videos on the internet, much like this one. So this is something I'm a little experienced in. I'm building out a side project called StreamFusion at the moment, which is kind of like DataFusion Comet, but trying to accelerate Flink. And then also, last but not least, I'm a full-time software engineer at IMC Trading, which is a quant trading firm. Before that, I worked at Google. In my job, I mostly work all over the Iceberg stack. So I wouldn't really call myself a DataFusion expert, nor a DataFusion Comet expert, nor necessarily an Iceberg expert, but I'm kind of at the intersection of all three at the moment, just a little bit. So that's why I'm making this talk in the first place. I feel like in order to talk about Comet, I inherently have to mention Spark. I don't really know how much intersection there is between the DataFusion community and the Spark community, but when I think of distributed data computing, I think of Spark in the first place. It's pretty much been the de facto standard for the last 10 plus years. And inherently, as popular as it is, it's ultimately a JVM-based execution engine. And that's part of what DataFusion Comet is looking to improve upon. So Spark is distributed. You've got one driver, multiple executors that are doing work and passing rows of data between one another and doing any sort of SQL operations. So it's inherently something that we want to improve upon and speed up where possible. So I guess the point is, like I mentioned, Spark is decently old at this point, and you can see that it kind of operates on a row-wise execution model. So Spark operates on what it calls its own internal row. And when you issue a SQL query, like the one that I have on screen over here, internally, that's probably going to get code generated down to something like the code I have on the bottom, where you can see as you iterate through these individual rows in your data query, you're going to be running multiple projections or filters or any sort of operation within that iteration. And while intuitively, as computer scientists, we might think that that's the best thing to do, it's not always going to be the case. We might actually be better off operating in column batches. Now, I assume that I'm kind of preaching to the choir a little bit here, talking to the DataFusion community, but I'm inherently going to share this video with some Iceberg people as well. And just to get them on the same page, we can get a lot of really good performance gains by operating on column batches instead of a single row at a time. So while the code on the left kind of looks a little bit silly because you're like, well, I have to operate over this data 4 separate times to do something that I could normally do with a single for loop, the reality is that depending on how you write that code and how you compile it down, you can take advantage of a lot of modern execution features. For one, we can use SIMD instructions, which stands for single instruction, multiple data, and get effectively free parallelism over a CPU core. Number two is that we can basically do CPU cache prefetching. Because the data is itself organized in a flat memory buffer and you're iterating over that buffer, the CPU is going to pull in data that it's about to operate on prior to when it normally would. And as a result, we get some performance benefits there. Now, while I've spent the last couple of minutes talking about how Spark is kind of old and you're using the JVM and doing garbage collections and you're operating on rows, it doesn't mean that we necessarily want to get rid of the whole thing. I mean, for starters, a ton of people already use it. But besides that, it has a super mature SQL parser, optimizer, it continues to do adaptive query execution during the actual runtime of the query. And it's distributed, which is not something that's necessarily trivial to build out. Like DataFusion itself is something that you embed within a single node. So because all of these things that are in Spark are not necessarily going to be in the critical path of a query operation, it's going to actually be really useful for us to kind of keep these around if we can, but then also use DataFusion where it really matters, which is the actual execution. It's also not to say that we couldn't get really nice performance improvements by improving on things like query optimization and AQE, but DataFusion, at least as far as it goes in Comet, is mainly focused on the actual execution itself. Another really important thing about Comet is it wants to be, kind of drop in and replace for existing Spark jobs. Meaning, as long as you can just flip on a switch that says Comet enabled, your inputs and your output to that job should be exactly the same and byte identical. So just to give a very brief history of some Spark accelerators that have popped about in the last few years. For one, there's Rapids, which is basically NVIDIA's attempt to keep the Spark interface but do execution on GPUs. There's Photon, which is Spark on C++ that came out of Databricks. There's a really nice white paper on it that you can read. And then another two that are open source that are a little bit more recent is Gluten, which is mainly driven by Intel, but it's Spark on top of MetaVelox, and then Comet, which is Spark on top of DataFusion. And that's kind of being championed by Apple quite a bit. So basically, the idea here is, when you run a query on Spark, it's going to generate some sort of query plan with a bunch of different operators, and we can actually re-implement those operators in order to accelerate them and make them faster than they would have been in the JVM execution. So this is a super, super high level overview of what Comet's architecture really looks like. But basically, the idea is that Spark continues to do all of the control planey type of things, planning the query, orchestrating it, spinning up executors. And then on each executor node, you're effectively running an embedded DataFusion instance that can process columnar data, typically in arrow batches, and make the job run a lot more efficiently. So if I give a really basic example of what query planning might look like between Spark and Comet, you can see that for this query in the middle of the screen, I've got the Spark plan on the left and the DataFusion Comet plan on the right. So because of the fact that Spark actually processes data row-wise or row at a time, one consequence of that is that a lot of queries that are run on top of Parquet files have to pay an expensive transpose operation to convert that internal Parquet columnar format over to rows so that Spark can then operate on them. Especially for wide tables, this is another penalty that we don't really want to have to pay. On the contrary, Comet is operating on arrow batches, meaning that we're going columnar at a time, and you don't actually have to pay this transpose between Parquet and arrow batches. It is a much cheaper translation. Arrow is, an open format in memory to represent column batches that's become very popular these days. DataFusion also generally operates on it. So how do I get into Comet? Well, basically, like I mentioned, I do a lot of Iceberg work, and Comet seems like the best way to actually accelerate a lot of Iceberg jobs. For those of you who don't know or don't use Iceberg very much, I feel like Spark tends to be kind of the first class query engine implementation for a bunch of Iceberg jobs. And so because Spark supports all of these Iceberg features, being able to trivially drop in a Spark accelerator is going to make my boss hate me a lot less when I'm hogging all of his compute. So what actually is Iceberg for those of you who are not too familiar with it? Just to give a really quick overview, Iceberg is basically just a standard metadata layer that organizes a bunch of files into a table. Now, it's evolved since then to add a few different new features. For example, things like row and column tombstones. Column tombstones are coming soon. You can do efficient metadata pruning without actually having to read particular Parquet row groups. You can do time travel and jump to a previous version of metadata. Generally, things are stored on object store, whether it's the data and the metadata. You can do things like schema evolutions without actually touching the data files and partition evolutions. And then most importantly, you can throw a bunch of files in and remove them from the table atomically by virtue of just updating a single pointer in your Iceberg catalog. Now, like I mentioned, Spark is kind of the standard Iceberg query engine, but Iceberg is supported by just about every analytical query engine at this point. DataFusion is no exception. But whether it's Dremio or Spark or Trino or Presto or any of those, you're likely going to see some sort of Iceberg implementation to be able to read those tables. So fortunately for me, Comet actually already is able to read Iceberg tables. Basically, the way that it does this is really intuitive. It plans the query like it normally would using the Spark Iceberg reader, which at this point allows it to pick out all of the data files that it actually has to read, given the filters and after doing things like metadata pruning. Once it does that, it can basically hand over all of these tasks to the executors, which are then going to fetch the corresponding Parquet files, convert them back into arrow batches, and then process the actual query. So this is really great. And it also means that we can use something like Iceberg Rust on the actual DataFusion nodes themselves in order to do things like applying delete files or executing any custom Iceberg logic. Now, one thing that has been missing up to this point in Comet, and I've seen a few tickets on GitHub in order to implement it, and it's also very relevant for me, is to be able to write Iceberg data. For now, right now, like I mentioned, Comet is read-only when it comes to Iceberg, and this is something that we'd really like to implement. One of those reasons is, for starters, I run a lot of ETL jobs on Iceberg, and my compute bill is getting pretty expensive. Number two is when you have Iceberg tables, if you need to sort them or you need to compact them, it would be really great if we didn't have to transpose all of those arrow batches back to rows in order to then just go ahead and write them back to Parquet. For people who are maintaining huge tables, and something like S3 tables immediately comes to mind, who's really invested in the Iceberg Rust space, you would think it would be really impactful for them to be able to do compaction jobs, but in a much more efficient native execution style. Cool. So let's just take a very, very quick cursory glance over what Iceberg writes in Comet currently look like. On the left, basically what I'm showing you is a query where you're reading in Iceberg data, you're doing some sort of operation, and then you're doing some ETL job to ultimately flush this out back as an Iceberg table. As you can see, all of these projections and filters are still implementable and executable as DataFusion operations. But then right before you write the data, you basically have to transform or transpose all of those arrow column batches back to rows only for the Spark typical Java Iceberg writer to then serialize those back as Parquet files, which is implicitly doing the reverse transpose. To me, that's a big waste, and it's something that I want to get rid of. So as you can see, I've gone ahead and put up a review that is basically saying, hey, rather than take this data, convert it back to rows, and then write it out as Parquet files, which is wasteful, why don't we keep that data in arrow batches this entire time, and then use Iceberg Rust, which can trivially take arrow batches and flush them out as Parquet files. So now we're just going to get a little bit into the implementation of how my proposed feature works. Basically, in terms of the objectives that I'm trying to make sure this feature request is sticking by, number one is that it has to be faster. Number two is that we want to avoid that extra transpose that I was talking about in the previous slide. Number three is that generally speaking, we want to continue to let Spark do a lot of the control plane operations. I want to have Spark deciding where these files get written. I want to have Spark interacting with the catalog. I want to have Spark, and specifically the Java Iceberg API, writing things like metadata files, which wouldn't be accelerated as much by Rust. But what I do really care about is accelerating specifically the part where we're writing Parquet from our arrow batches, which is basically the critical path of this execution of the query. And number four, and most important, is that I want to stick with the ethos of Comet generally, which is I want to ensure that I'm only accelerating queries where I can get exact parity with Spark's Java Iceberg implementation. Otherwise, I'll fall back and let Spark do its normal thing. Cool. So just to learn a little bit about what Iceberg writes look like in Spark using just the typical Java path of executing these. Basically, this is known as a V2 write. And so V2 writes in Spark package both all of the writes on all Spark executors, as well as a single commit operation from the driver at the end of it. And so basically, while that is a very nice interface and it has many implementations beyond Iceberg, many different table formats, things like databases, other implementations beyond that, it actually makes it a little bit hard to accelerate that with Comet because the actual data writing and the data committing have been fused together into a single operator. Now, what Comet actually does is that it only looks to accelerate operators that are within the adaptive query execution block of a Spark query. And so this is not the case, and we have to think about how we can actually split this functionality out in order to accelerate it. So just to basically look at what we end up doing here, I've basically decomposed the existing Spark v2 write into two separate stages. One is going to be the Iceberg write, which, like I mentioned, is effectively the data rows coming in and being written to Parquet. And then the second is going to be the Iceberg commit. Now, I've moved the Iceberg write to a different piece of the query itself so that it's basically within the adaptive query execution part of Spark. This is really important because as AQE runs, the plan shape may look differently during query time, and we may no longer want to make this part of the query a native operator, right? If something upstream was not necessarily column-oriented anymore after AQE running, then we would need to know that so that we could change our Iceberg write operator as well. Another nice benefit of this is, of course, that we can accelerate it, and we're just going to go ahead and talk about how. It was fairly easy to break these things up to a separate operator because Iceberg fortunately has public classes that allow us to basically recreate these Spark operators that are separate but still doing the writer and committer step. Okay, so what does the Comet accelerated Spark write really look like? Well, at a high level, basically, as you can see on the left side of the screen, we've got our Comet Iceberg write over here. And when we actually plan out this query, we're going to initialize a particular writer task on the Rust side by handing it a bunch of writer settings that correspond to the Iceberg settings of the particular table. And we're also going to hand it an arrow batch iterator so that it can start pulling in arrow batches from upstream operators in the query plan. As those arrow batches come in, effectively, our native operator here is just running Iceberg Rust code so that we have the freedom to tinker with things like Parquet writer settings and exactly where the write is going to, and then ultimately flushing those Parquet files back to Amazon S3. Once all of those arrow batches are exhausted, we send back a bunch of data file stats back to kind of the Java operator. And we do so in the form of Iceberg manifest bytes. The reason being that that's a standardized format of data that both the Java API and the Rust API can understand with one another. Once all of these Comet Iceberg write tasks eventually finish, they each send task commit objects back to the Iceberg commit operator, which commits again from the driver. So like I mentioned before, it's really important that we produce complete data parity with the existing Spark implementation of writing Iceberg. If there's anything that concerns us about a user's writer settings or table settings, then we want to be able to fall back so that we don't actually, corrupt their table or just silently produce different data than they would be expecting. So because we're using the Iceberg Java API and ultimately comparing that to the Iceberg Rust API, the latter is a little bit less mature than the former, and there's quite a few Iceberg writer properties that Iceberg Rust doesn't support that Iceberg Java does. So we have quite an exhaustive list and list of test cases as well to ensure that if any of those are set beyond what Iceberg Rust can support, we'll fall back to writing the normal way, which is unfortunately a little bit less efficient. For example, at least as of the time of me building this feature, Iceberg Rust, I don't believe, was able to write any positional deletes or deletion vectors. So if you have a query that requires writing those, we're unfortunately going to have to fall back and continue to do it in Java. Cool. Since people care about this, just a very quick, simple benchmark that I took on my laptop, which is obviously the right way to do it. You can see that having Iceberg readers in Comet is already impactful over having, so column A is basically saying, I'm going to read in a bunch of Iceberg data using Spark and write it out using normal Spark. And you can see that takes about 16 seconds. All of a sudden, I enable Comet, and then I start reading in that data using Comet, processing it, and then writing it back using the normal Spark APIs, which means we have to do a transpose and then write normal Parquet files using Java's Parquet writers. You can see there's still a significant performance improvement, but ultimately where we end up getting the best performance, and the reason I care about the reader and writer case is because this is what you're doing in ETL jobs, this is what you're doing in Iceberg table compactions. You can see that this is where we end up getting our most efficient performance gains. Now, obviously, that's when we have a fairly wide row. As the row size decreases, there is less of a penalty of doing a columnar to row-wise transpose, and vice versa, going back from rows to columns. And so you'll see that performance gap dissipate a little bit. So yeah, thank you all for coming. I've linked the DataFusion Comet pull request below. I've already had some eyes on it, and I'm starting to split it up a little bit as well to be a little bit more palatable towards reviewers. But you can see I've got a full big Spark plan right here, and ultimately this new Comet Iceberg right at the bottom, which is accelerated. Now, it looks like I've operated for about 19 minutes here, so I just want to do a very, very quick live demo if my Jupyter notebook here is still working, which is basically me going to sort an Iceberg table. Let's see, and the session is closed. The demo effect gets me again. Well, if I can't, I'm going to go from there. Fortunately, I already pulled up a cached plan, but this is what a sort operation would look like when you're doing compactions. So you can see now that we're scanning the data with Comet. It's completely native. We're doing an exchange with Comet. So now we're doing a native shuffle of arrow batches from node to node. We're doing a Comet sort. So again, this is still operated on in DataFusion. And then finally, a Comet Iceberg write, which means that Iceberg Rust is itself taking arrow batches, flushing to Parquet, sending commit metadata down to the driver, which then commits it like Iceberg Java normally would. So I appreciate you guys all coming. I'll stop sharing the screen, and then if you have any questions, feel free to let me know.
Great work on this, Jordan, and
Thank
excellent
you.
presentation. Would you mind throwing that PR link into the chat? I'm not sure if everyone caught the.
Yep, will do. I appreciate it.
Cool. Any questions for Jordan? We'll sit here in awkward silence for 30 seconds and then move along.
My favorite.
No questions. One comment. Yeah, really excited about the Iceberg writes. So Andy Grove work on the Comet project. We have an issue with bandwidth for PR reviews. We are excited about it. We will get to it. Thank you for your work.
Thank you. I appreciate it. Thanks for saying that.
Yeah, Eric here. Thanks for the Good job. Curious if we have done any broader benchmarking, like TCP DS dataset, like.
I have not done it for TPC. I'm actually, you know what? I'm not sure off the top of my head whether those include writes as well in that, or
Yes,
if it's
those are
just
most
queries.
likely. Yeah.
So I
So
was going to say I haven't done too formal of benchmarking empirically at work because I'm maintaining my own internal fork on a very wide data set. I'm seeing, like between 5 and 10x speedups, but that's because it's a particularly wide data set. Somebody just reached out to me on LinkedIn to say that they're going to do a formal benchmark of it. So I'll circle back when they actually do that.
gotcha. Thank you. Yeah, I was reading that AWS has they did some benchmark. That's the link for Comet and the TCP/DS. But I believe they will use the older version, not using your change yet. So
Yeah, this one is still in review. So we'll get there eventually.
cool, awesome.
Thank
Thank
you.
you.
Yeah, I'm hoping this will be really impactful for compactions. The larger people get their tables, especially at terabyte, petabyte scale and larger. Compaction takes a bunch of compute, and I have certain tables where doing this transpose is just kind of infeasible. So it's been impactful for me.
Cool. Any more questions or comments for Jordan? Going once. Okay. Awesome. Thank you, Jordan. Appreciate it.
Awesome. Thank you.
Good job. All right. Phillip, on to you.
All right. Thanks, Wyatt. And thanks, Jordan. It's funny how these presentations, these community showcases seem to be themed. We had the geospatial theme last week, and now we've got the distributed compute theme this week. So let me share my screen. So I'm Phillip. I'm from Spice AI, and I'll be sharing a little bit about how we've built a highly available distributed query engine on top of Apache Ballista. So kind of where Comet is accelerating existing Spark jobs, Ballista takes a different approach of, we'll just build, a native distributed query engine on top of DataFusion. And I'll be showcasing a little bit about what we've done to, build that into Spice and kind of achieve what I'm showing here on the right, which is basically how do we have multiple active schedulers being able to process queries at the same time and share a pool of executors and make sure that, if we say that we accept a job from a client, even if one of those schedulers goes down or disappears, we'll still run that query to completion. So a little bit about myself. I'm Phillip. I started my career at Microsoft, was there for about 8 years, spent a year at GitHub on the GitHub Actions team, and then co-founded Spice along with Luke back in 2021. And as part of Spice, I've had kind of the opportunity to work on a bunch of these different open source ecosystem projects that you see here on the right, focusing a lot on Ballista at the moment, but I've also contributed to DataFusion. We're the maintainers of the table providers, DataFusion table providers repo over on the DataFusion contrib. And so just had a lot of opportunity to contribute to the community. And so as we were doing this work on building on Ballista, looking forward to keep contributing upstream as well. Last time we announced Spice 2.0, and you can think of the major theme for that for us is basically we wanted to address, in addition to other things, one of the things we wanted to address were these kind of single node ceilings. So single node analytical query engines have gotten really good in the past few years. So we've had, started off kind of with DuckDB, where you could run all these analytics on your local laptop or on a single node, and then DataFusion kind of becoming this best-in-class single node query engine, which is really good for, if you can have everything on the single node, but, once you start getting to these larger jobs, like was alluded to in the last presentation, is you start to hit this capacity limit. It's like, well, what do you do after that? Like you'll go to Spark, but there's a lot of operational overhead with operating a Spark cluster. And so one of the things we wanted to address was, how could we take something that has kind of the simple and familiarity of the single node engines that people love, like, it's very operationally very simple, and just basically scale that into being able to run larger jobs on multiple nodes. And the other thing we wanted to address was basically how do we make this fault tolerant? So if you are running this in production, you don't want, a single node, you don't want to have a single point of failure. So if one of your nodes fail, you want to be able to recover from that. So why did we choose to build our distributed query on Apache Ballista? We actually looked at a couple of other options. Actually, when we were thinking about what we wanted to do here, we were visiting the Datadog office in New York, and they're the people that created the DataFusion distributed project, which is, if you look at it, it's very similar to Ballista. It has some of the similar goals. It wants to basically make DataFusion execution distributed, as it says, but it's more focused on being kind of a toolbox where it gives you some nice primitives to kind of build your own distributed query engine. But it leaves a lot of the kind of semantics of like, what does it mean to be a cluster? How do you handle failures? Kind of up to you, and you'd have to build a lot of those features yourself. The other option we consider is basically, you build it fully ourselves. That was going to be a big build. And then, so that's kind of why we decided to settle on Ballista, because it already had a lot of the features that we were going to need to build, including, batteries included, schedulers, disk-based shuffles, stage retries kind of automatically implemented, and then just inactive community. So like, I think right now on the Ballista community, we're working on adding, adaptive query execution, which is going to make Ballista even faster. A big thing for us is we wanted to kind of bet on the Apache community. That's worked out really well for, DataFusion. DataFusion's kind of really exploded in popularity and had amazing community contributions over the last few years, and just making it kind of the best in class single node engine. And so we want to do that for Ballista and kind of make it, the best in class multi-node distributed query engine as well. So here's a little bit of a sampling of things that we've implemented on top of Ballista. So we've improved scheduling for, we use poll-based scheduling. We've had, one of the missions for us when we were building this is we wanted to make it as simple as possible to operate. And so we've kind of made it where, the schedulers are the kind of single source of truth for the entire cluster, and all the executors just pull state from them. All of the communication between the cluster nodes, between the schedulers and the executor, are using MTLS by default. This is actually one of the first features we ended up upstreaming back to the Ballista project earlier this year. We have the ability to choose which shuffle backends you want. So shuffles are in DataFusion and in Spark. Whenever you get to the end of a stage, which are basically just how you break up the query into multiple pieces, when one of those pieces ends, you have to write kind of the intermediate result somewhere. And so Ballista currently just writes that into local disk. And we've added the ability to kind of to choose if you want to persist that to local disk or into memory, or write it back into object store so that you can actually have ephemeral execution. We also implemented support for shuffling into a different data format. So right now, Ballista will shuffle in using Arrow IPC, which is the same format that you have Arrow in memory, but it's quite big when you write it to disk. And so by writing to Vortex, we can get these smaller intermediate shuffle files, which translates into less network and disk IO, at the trade-off of, more CPU in order to write those shuffle files to disk. And we've also actually implemented a bunch of custom plans on top of Ballista. Ballista, like DataFusion, has a bunch of extension points where you can say, I want to have custom execution nodes. We actually have implemented support for Iceberg, reading Iceberg tables using Ballista and Spice. And so I know that's something that might be interesting for the community. And so we could work on, upstreaming some of that support as well. And, just making Ballista really useful for the community. So I'll focus most of kind of the technical portion of the talk on, how did we actually achieve the goal that we set out at the beginning of the multiple active, highly available scheduler nodes. And so Ballista actually had taken a shot at this a while back. I was looking through the PR history, and in about 2022, I think some of the people from Core Logix were working on Ballista, and they wanted to have a similar property here where they wanted to be able to run multiple schedulers and have high availability that way. The way they implemented it was basically by using an external state store. So they had, I think we're using etcd, and that's kind of typically how most of these cluster engines work, where if you want to have high availability, you'll typically have like an active node and then maybe some passive nodes, and then you'll have to have a coordination service that can handle failover between them gracefully. But again, for Spice, we wanted to try to make this, operationally as simple as we can, as we could, and we rely a lot on object store primitives. And we actually really kind of taking a bet on object store as being all you need. You're already going to be using object store for reading your data files, and so by just adding this one extra dependency on object store for storing some coordination state, we automatically get a lot of nice properties from that. And so one of the big features that object store adds is this e-tag conditional writes, which basically means if you want to make an update to an object in object store, you can say, well, I want to make this update, but only if the object hasn't changed since I last looked at it. And by having that property that we can rely on, that gives us some nice features. So like, for example, let's say that scheduler A gets job 1, it accepts that job and it starts running it. If scheduler A dies and it writes its job metadata into object store, it's also writing its heartbeats into object store. What can happen is that both scheduler B and C can monitor for the heartbeats and the job metadata. And when it detects that, scheduler A's heart is not heartbeating anymore, then it must have failed. It's no longer part of the cluster. I need to go reclaim any of the jobs it was working on. And so both scheduler B and C might say, oh, this job J1 is running on scheduler A. Scheduler A doesn't exist anymore. I need to go reclaim it. They'll both submit a request to basically take ownership of that job to object store. Only one of those are going to succeed. So even if they both race at the same time and say, please let me take over this job, the object store primitive for conditional writes is going to guarantee that only one of those will succeed. And so whichever scheduler succeeds will take over that job. It'll fence it so that even if scheduler A will increase the epoch on that job metadata. So even if scheduler A comes back and starts to try to execute it, it'll realize, oh, I don't have ownership of this job anymore. And so that's what gives us the ability to kind of, gracefully fail over, active jobs between these different schedulers. The other nice property about using object store is the schedulers don't actually need to talk to each other. So the scheduler A is not like gossiping or reaching out to any of the schedulers. So it doesn't really need to talk to them because it writes its own topology information into what we call a cluster.json, which is basically kind of the master document for who's participating in the cluster at the moment. And so scheduler A knows that scheduler B and C are part of the cluster because they've all written into this cluster JSON saying, okay, here I am, here's my address information, here's how you can contact me. And then it uses that when it's kind of, talking to the executors and say, here's all the other schedulers that are part of the topology. And that's how we basically solve the problem of topology discovery. So again, one of the nice things about this is that object store becomes the only extra dependency, which you probably already have if you're reading data from object store. And so that allows us to kind of get away with not having an extra consensus service and achieving kind of the multiple active schedulers. The other problem you'll run into when you want multiple schedulers, though, is how do you make sure that you don't push too much work to the executors? And so Ballista has kind of two modes where you can have push scheduling, where this Ballista scheduler will actually, when it's doing its planning, it'll figure out, okay, I've got this big query, I need to break it up and assign it to different executors. Currently, what it does is it has an in-memory view of which executors are working on which things, and it uses that as part of its planning to say, okay, well, executor 1 pretty busy. Why don't I give this to executor 2, and it'll actually push that work. It'll call out into executor 2 and say hey, I'd like you to work on this query. That doesn't work when you have multiple schedulers. If they all have kind of independent views of which executors are free or busy. And you would either need to solve that by, having some sort of global view, whether that's, slot leasing is one idea where you basically have the schedulers say like, hey, I would like to, run this job that needs 10 slots. I'm going to try to get leases on those slots from the different executors, and the executors will promise not to, use that slot for some other job until I give it work. And that was actually one approach that we were considering early on. But again, that goes back to you need a coordination service, and for this particular use case, object store doesn't work very well because the actual like execution, like how much work is being done, changes quite often, and so that's not a great use case for the object store latency, which is about 100 to 200 milliseconds per write. And so you're going to be completing jobs hopefully much faster than that. And so we wanted to kind of a different approach. What we ended up going with was basically the poll scheduling model for Ballista, which has the nice property of executors kind of know their own capacity. They only poll whenever they're free. If they're busy, they're not going to poll for more work. And so that gives us kind of this nice self-regulating property where the executors, if they're already busy, they don't ask for more work. And on the scheduler side, instead of kind of pre-assigning work to executors, instead of saying like, hey, I've got this query, I'm going to assign it to executor B, what it'll do is say, I've got this query, I need somebody to run it. And then the next executor that calls in saying I have capacity to do some more work, it'll just say, oh, great, I've got some work for you to do. And so it doesn't pre-assign the work to executors. And so that means that the schedulers don't really need to know how busy the executors are, because they'll just say, as soon as I have work for you to do, I'll just give it out to the next person that asks. So that gives us kind of that nice property where the schedulers don't really need to know what the executors are working on, and executors can call out to all the schedulers to ask for work whenever they're free. One thing that we added on top of Ballista was this ability to kind of interrupt and ask for a poll now, because one problem with polling is if I just polled a millisecond ago and then we've got a job come in, well, now I have to wait for the whole kind of latency of the poll before we'll actually start execution on that job. And so we've added the ability to say, okay, we've got this job come in, let's broadcast this poll and say like, hey, I've got some work for you to do. If you're not busy, please come pick it up. And so, yeah, but between kind of these two ideas, we were able to build the multi-active scheduler where we don't have a single point of failure. Schedulers can share the executors. And so even if one executor goes down, the scheduler that's driving that task will just retry it on another executor. One of the schedulers goes down, we'll retry it on another scheduler that's running in the cluster. So that's HA. Another thing we wanted to do was basically have secure communications between the different nodes in the cluster. And so scheduler to executor communications, and also executor to executor for the shuffles. So we've added support for basically MTLS by default. MTLS, if you're not familiar with it, is mutual TLS. It's where both sides of the connection authenticate using certificates. So typically in regular TLS, only the server needs to present its identity and say like, hey, I am actually the server, you can trust me who I am, but the client doesn't need to present anything. Whereas with MTLS, both sides need to authenticate and say like, I am who I am here, and you can trust that because we were both issued certificates from the same certificate authority. And so the reason we wanted to do that is we wanted to basically guarantee that nobody could participate in the cluster that wasn't an authorized member. And that lets us do things like have centralized the configuration on the scheduler side. So the scheduler is the only one that needs to know which data sets are part of the catalog, which secrets do I have access to, and then the cluster can basically just ask for, the cluster configuration can ask for secret values it needs in order to initialize any components, and it also calls up to the executors to get the other schedulers that are part of the topology. And just check how I'm doing on time. Okay. Yeah. So as mentioned, the shuffles, we've added support for both memory and object store. They have different trade-offs, as you might guess. The latency for memory is a lot lower, but the trade-off then is now if a executor goes away, then you've lost that shuffle and you'll need to retry it. Object store shuffles have the nice property of it keeps it a lot more ephemeral, where as soon as we complete stages, we'll write those shuffles out to object store, but there's a lot more latency involved with that. And so this might be good for if you're running, really long running jobs where, retrying from start would be very painful, whereas it would be less good for, jobs that you expect to complete quickly. So with that, I'll switch over to a quick demo of how we actually do this failover. All right, are you able to see, my window here?
Yes.
Yeah. Okay, great. So what I have here is basically kind of I'm staying all in the terminal for this, but I've got this terminal UI that is going to kind of visualize what's going on. We've got 2 schedulers that I'll be running as part of this demo. They'll have one executor that they're sharing. So I'll just go ahead and start the cluster. So I've got a little script that will start it up, and we can see that we've detected both schedulers are running. We've seen their heartbeats. And so this heartbeat is basically them writing into object store saying, hey, I'm still alive. I'm still alive. I will run this command. So we've got a CLI that allows us to kind of submit jobs to the Ballista cluster using SQL. So I'll just connect, my local ports are different here, so I'll connect to both schedulers. And just to show that it's working, I'll run a query, very simple query. We can see that scheduler 1 drove that query, and it succeeded. If I come over here and select 1 over here, we can see that scheduler 2 drove that query. So that kind of shows the multiple active things where any of the schedulers can accept queries and run the job to completion. But if I run a slightly larger query, so this is an aggregation, it'll take, I'll let it run. It'll take about 12 seconds to run, which should give me enough time to actually show what I want to show here. But so this query will run. We get the results, 50 rows, and it ran to completion. So if I rerun that query and I have some controls here to basically kill the current scheduler that's running, excuse me, I'll run this query. I'll stop listening for it on that scheduler. I'll wait for it on this side, and then basically crash the first executor, and we'll see that it was running it. It's not heartbeating anymore. The second scheduler is going to eventually notice that this job has been orphaned. It'll recover that job. It'll fence it so that the scheduler can't reclaim it, the original one, and then it'll run into completion. And so here I get the job run to completion by just waiting for the results from the second scheduler. So so that's kind of a quick demo of things. This took a little bit of time because we had to wait for the heartbeat to expire. I'll show kind of a separate version. I'll just reset the cluster where if the scheduler can gracefully shut down, we don't have to wait for the heartbeat to expire before we take over the job, because the scheduler itself can know, like, oh, I'm shutting down, I should hand off all my work to the other clusters. So I'll restart this, and then I'll rerun this query. I'll wait for it over here, and then I'll actually gracefully kill the scheduler here. We can say that it was deregistered, gracefully left the cluster, and then it recovered basically almost immediately that job, and is able to run it to completion over on this other side in a second. There we go. So that kind of a quick demo of the HA capabilities that we built on top of Ballista using Spice. Let me switch back to my slide. So on this slide, I'm basically showing all on the left are all of the fixes that we've made into our, we maintain our own fork of Ballista. And so all of these numbers on all these boxes on the left are all the fixes we made into our fork around those different categories. And then on the right are all of the fixes that we've started to upstream into the upstream Ballista project. Andy Grove is actually on the call today. He did a great job of yesterday. He actually opened an issue kind of listing all the things that we might be able to take from, he might be able to take from Spice into the upstream project. Turns out a lot of these issues were already, I think, solved in different ways in upstream. And so, going forward, we'll do a better job of making sure that, as we, want to improve Ballista, we'll contribute those fixes back, with eventually the goal, hopefully, of being that we're not actually running our own custom fork, because everything we need is in the upstream Ballista. Some of that will require a bit of design work to figure out, how do we get the extension points that we need for implementing some of the things that we want in Spice, as well as just, general fixes and improvements. So yeah, if you're interested in getting started with Spice, I've left some instructions here. We have a cookbook recipe that will kind of tell you how to get started. It's very easy. Just download the binary and you can run it like I just showed. But yeah, I will open it up for questions.
Nice job, Phillip. Alex, using the raise hand functionality, I like it. Go ahead.
I come from a world of Google Meet, and maybe that's not appropriate for Zoom. But thank you so much for this excellent presentation. I'm really excited to learn like the kind of philosophy and engineering behind Spice AI. Your orientation towards high availability, do you think that makes Spice suitable to work in highly preemptible environments or like decently preemptible environments?
Depends on how preemptible you're talking. If you mean like spot instances, potentially, I would say that we've more really focused on this for basically people that kind of need rock solid, high availability in production. And so while you'd probably use it for those use cases, we haven't really, that's not our main kind of design focus for it. But I imagine it would work pretty well. Because even if the entire cluster dies, all of the important state is stored in object store, and so it can basically resume from any point.
That's awesome. I might reach out to you to discuss this more. Thank you so much, Phillip.
Sure.
Cool. It looks like there are a few unanswered questions from Sarah. Luke has been navigating the chat. Sarah, feel free to unmute. Otherwise, I'm happy to share your questions. I'll give you a couple seconds here. Okay. First question from Sarah was, one question on the retry. How does the driver even decide when it's worth retrying and when it's not?
So that's actually part of Ballista itself. So that's something where we kind of lean on the existing Ballista semantics. So the Ballista has its own kind of scheduler service and is keeping track of all of the active jobs. All we've done at Spice is really just, hooked into the existing extension points that let us basically store and resume from those checkpoints. I believe how it works is basically the scheduler is basically keeping track of all of the running stages that are running on the executors. And if the executor reports back that it failed, or if the executor dies, because the scheduler also keeps track of the heartbeats for the schedule or for the executors. And so if it knows that an executor is working on one of its tasks and the executor doesn't heartbeat for a while, it'll kind of assume that the executor is dead, and then it'll automatically kind of retry that and schedule that stage onto a different executor to get it to execute. Does that answer your question?
See a thumbs up from Sarah. And then Sarah's second question, or I guess prompt was, could you talk about the memory management done in Ballista?
Yeah, so I think this is still an active area of work. I think I even saw a PR from Andy today improving this aspect of it. But we've memory management, even for single node DataFusion, is kind of an important thing that we spend a lot of time on trying to optimize, because there's a lot of pieces where even if you have like DataFusion is aware of all the memory that it's using, but if another component, which is not hooked into that view, also tries to use memory, then you can end up in a situation where you end up overcommitting. We actually had an issue where initially executors wouldn't have any memory management at all, so it would just kind of operate in the default DataFusion mode where they just use as much memory as they could and then eventually run out. In our version of Spice, we kind of publish those memory limits from the scheduler. So you would set the memory limits on the scheduler, we would publish those over to the executors, and then we basically just hook that into the native DataFusion memory management flow. Because at the end of the day, like after you distribute the stages, it's kind of just relying on a lot of the native DataFusion execution to control that. So for the most part, we just make sure that DataFusion knows what memory limits it can use, and then we just make sure we pipe it all through. But yeah, I think there's more work that could be done on Ballista specifically to make this scenario work a lot better.
Thanks, Philip. I believe we've exhausted all of the questions in the chat. Any other questions or comments before we close? Oh, here we go. One more from Sarah. Let's see here. The high available scheduler is interesting. Was it motivated by the fact?
I might be able to
on how to recover
this question. So
go ahead.
I think there's like two parts of this. So hi, I'm Luke Kim. I'm the founder and CEO of Spice. But we endeavor to be as customer obsessed as possible. And so what we heard when we went out to test and get signal from the market is that one of the biggest pain points with several of the products out there today, for example, one of the potential customers we were talking to was using Dremio, was the single coordinator issue, and you can do HA, but it's like HA failover. And so we also heard that in kind of various other mechanisms for other products as well. So one part of it was just like customer driven. And the other part of it is that Phillip and I have been working in distributed systems for like 10, 15 years before this. And so we just always have a very high availability distributed systems mindset with everything we do. So put those two things together and hopefully we made a good product. So maybe you can use Spice.
Yeah.
I think like somebody's asking about val key. Is that Malay? So is this the, yeah, sorry. Go ahead.
Yeah, so my question was more, I think this could be framed as an interface, and then this would be the object store implementation of that interface. So because implementing this on val key could have its own benefits. I was just curious, is there any reason why this is kind of as a hard dependency on object store as a apart from being an interface?
Yeah, I think as I mentioned, if we can find this slide. Yeah, so we kind of decided to take a bet on object store because we saw that it, disaggregated compute is kind of a big trend right now in databases where you separate the compute from the storage, and a lot of people are using object store for that. Services like Turbo Puffer, they've kind of built an entire business around basically betting on object store. You're already going to have an object store dependency most likely, as I mentioned, and so kind of building this on top of object store team to make sense. That being said, like the extension points that we implemented to make this work on object store they are extensible. They're just an extension trait in Ballista. And I think we might have had to extend that a little bit, but for the most part, like you could just swap that out with, a val key implementation on your own project. And so if you wanted to use val key to store some of this stuff, like some of this stuff is not Ballista related. So like the work we've done around like topology and heartbeats is a bit custom for what we've done, and kind of implemented that outside Ballista. But like the core state of the job metadata is just a trait in Ballista that you can implement, and we just
actually have
implemented
a
it from
second
the store.
implementation, right, Phillip, which is, I think, just file. So we have two implementations today of that trait. One is object store and one is file. So you definitely could add like an additional one, but it would have to support the ability to do conditional write.
Yeah, I think just the reason why I was thinking about this is Valky has a lot of like very performant, options for what you're doing here. So it could be like more performant in some use cases, and then some orgs might have like very robust Valky implementations available to them readily. So like even if they have object store available, using an existing Valky implementation could actually be more performant in some cases. So you might even end up mixing and matching.
Yeah, if you already had the infrastructure to do that, then it's a great option.
Yeah, and if you already had that infrastructure, then the push scheduling option becomes a lot more attractive in that case. So then you can actually have that kind of global view of which slots are available, because you could implement that on top of Redis, which is obviously a lot more performant than object store. Okay, yeah.
Yeah, one of the other things Phillip didn't quite mention is if you look at the DataFusion distributed project, one of the things it tries to do is a lot more node-to-node communication without shuffles, because they wanted a much more real-time, higher performance level. And so we actually have another mode in what we actually did is use the Ballista topology and then still do a node-to-node communication over the top. And so if you were going down this route of like very high performance, using Valky and then starting to go to pushes and so forth, then you might also want to use that additional mode, which we call, what do we call it? Distributed
acceleration.
Distributed acceleration, where you're not doing kind of the disk-to-disk based stuff, or because once you kind of get into the longer running jobs where you're doing minutes or so forth, then hitting object store is not going to be significant in terms of your overall job time, and you're doing these big shuffles and so forth. But if you are wanting to do like very high performance node to node in memory accelerated query, but you still want it to be multi-node distributed, then you kind of get into that world and you go down this other path. And our goal is to support both, but using the same cluster topology that Ballista provides, essentially.